Today I'm excited to introduce our project, School World Classifier. Before we begin, let's take a quick look at the structure of our presentation. Here what we covered today: introduction and overview of our project and its objectives. Concept idea, the key ideas behind our classification system. The reason why we choose this process, why we decided on this approach over together, before versus after, a comparison of the old method and our improved system. For chart, a step-by-step breakdown of our system work. Coding, a brief look at the implementation of our program. Results, the outcome and accuracy of our system. Proposed idea for improvement, future enhancement, and possible and great. Lastly, team member. From introduction, sorting school board and nuts manually is time-consuming and prone to errors. This can cause inconsistency, making it less reliable, especially for large-scale productions. To solve this problem, we developed a computer vision-based classification system that's auto to sorting process, making it faster and more accurate. Our system uses scale conventions, thresholding, contour detection, and bounding box analysis to identify and measure each object. Before implementing this classification was inaccurate and size measurements were imprecise. Now our system can detect multiple objects at once and measure them precisely in real time.
Manual sorting of screw nuts and bolts is inefficient, time-consuming, and prone to human errors. Automating this process using computer vision can significantly enhance speed, accuracy, and consistency. This project aims to develop a prototype that utilizes image processing techniques to classify and measure screw nuts and bolts based on their size, shape, and distinctive features. So here are some key steps in classification process. Image acquisition. A webcam capture an image of the object. Pre-processing. The captured image is converted to grayscale, noise is reduced, and thresholding is applied to enhance object features. Feature extraction. Contours are detected, dimensions are measured, and tip shape analysis is performed to distinguish between screw and bolts. Classification. Objects are categorized into screw, bolts, or nuts based on extracted features. Result display. The process in image is annotated and saved with classification result. This approach leverages computer vision techniques to streamline industrial sorting process, making them more efficient and reliable.
Now, let's move on to why we choose this process to classify screws, bolts, and nuts accurately. We use several key image processing techniques: thresholding, filtering, image adjustment, perspective warping, and contour detection. Each plays a crucial role in preparing the images for classification. The first one, thresholding. In this term we use binary invert. This method is widely used in computer vision, including our project. It helps separate the objects like screws, bolts, and nuts from the background while reducing noise from unstable lighting conditions. The second one, filtering. We apply blurring and crossing filters to minimize noise caused by the environmental factors like varying light conditions, ensuring a cleaner image for processing. The third one, image adjustment and perspective warping. This step involves rotating, resizing, and cropping images to focus only on the target object. This processing improves classification accuracy by standardizing the input image. The fourth one, contour detection. This method allows us to detect objects boundaries, determine size and length, and classify the object type based on shape features. By combining these techniques together, we enhance image quality and extract meaningful features, enabling our model to distinguish between schools, balls, and nuts effectively.
Now let's look at the difference before and after using our system. Before we apply our system, the classification process was not efficient. The system used poor quantity samples, which make it hard to tell the difference between nut and bolts. It could not separate bolt from screw. The size and length measurements were not accurate. Also, it could only detect one object at the time. Because of those problems, the process was slow, unreliable, and not suitable for real-world use. With our input system, the results are much better. We use real objects for sample, which make the classification more accurate. The system can efficiently classify nuts and bolts. It separates bolts from screws. The size and length measurements are correct. Most importantly, the system can detect many objects at the same time, making it faster and useful for industrial.
Okay, so next we will be talking about the flowchart, the code, and the results of the backend or the main program of this project. So let's start with our flowchart. So this is our main function of the program. So we define our webcam and then check if it's connected or not. So if not, the program will stop. If it's connected, we will start the loop to start recording the frame of the webcam. So again, check if it's recording or not. If not, the program will stop. If it's recording, we will show the live feed of the webcam into the output. And then we define our current timeline. So this is where we use the current timeline. So we want the webcam to capture the image for every 3 seconds. And after that, we will use the time library to get the timestamp of the image. So we can use it to create the file name and then save the image. After save, we define the save path as test image, which we will use the test image variable in the process image function, which will process and save the process image in another directory. And this is where we want to stop the program by just pressing Q. The program will stop. If not, it will go back to the loop and then start the whole process over again and again and again. Which meaning that every picture captured from here, we will put in the test image and then save, which will then be processed again to the process image function and then save again. So this program will continue as long as we don't press the Q button of the keyboard. So this right here is the flowchart of each function that we will be using in our main program. So let's get started. Okay, so the first one over here is check nut. So we get the image from the prepare image function, then we convert to gray and we use half circle to determine which one is screw or bolt or which one is nut. So our next function is find dimension. This one we will just convert the dimension from pixels to centimeters for screw and bolt, and this one is for nut. The next one is classify screw or bolt. So we get the image from the prepare image, then we convert to grayscale. Then we use threshold to convert it into black and white, and then we use burn edge to get clear of the noise of the picture. Then we use control to find control around the object. So this is just to check if control found or not. So if not, return and the program stop. So if found, so we found the lowest point of the control, which is the tip. Then we'll be using that to determine which one is bow or screw by count the edge of the tip. So if the edge is less than 50 is screw, if more than 50 is bow, and then we draw the result and then we return the level which either screw or bow. Next one is prepare image. This function will be used to prepare the image from the main function over here to everything in the process part, like here also have one and here also have one. So what prepare image do is it will warp perspective of the image from the captured into the vertical, so the object will fit to the frame. Then we will use the threshold to convert to black and white, and then we crop into upper and lower image into 1 and 2. This one we'll use to check if the upper is head or the tip. So if the upper is tip, we will swap both of them. So this one right here we'll use to draw the transparent picture around the object, so we can get rid of unnecessary errors or noise. Then we return the picture to be processed. And this one right here is the process image, which is the main function we will be used in here. So what we process do is we load the image capture from the webcam, right? So we get the image, convert to gray, convert to black white, use crossing to get rid of the noise in the object. And this pixel over here is we will be used to convert from pixel to centimeters. Then we find control. After we find control, this is where we will be using the loop to get the control for every object in the picture. Meaning our program can be used to detect multiple objects at once, like multiple screw, bow, or nuts. Then we get the bounding box, we get the angle of the rotation, and then width and height. And this is just to check which one is width and which one is height. So after that, we will convert everything from pixels to centimeter. Then we use a check nut to check if it's nut or not. So if not, we will find the dimension nut and then draw the rotate bounding box around it. Then we draw the bounding box to the picture and then save it. Then return the save picture part into the program. And if it's not, meaning it's either screw or bow, we will use this find dimension to find the width and height, and then we use classifying screw or bow to get which one is screw or which one is bow. Then we draw the bounding box around the picture and then save, and then return the save part to the main again. So this here is our code of the program. So we import CV2, OS, time, NumPy, and Matplotlib. And this is where we define this directory for the capture image from the webcam. And this is where we define the directory for the process image of the process image function. And this is the width and height of the output window. So this one is the channel function. As I said before, we use half circle to get which one is either screw or bow or not. And this is the find dimension for both screw and bow, and this one is for nut. So this is the code for the classifying screw or bow. We get image, convert, blur, edge, find control, and this is for check if we get control or not. So we get the lowest pixel, then we calculate it to get the edge count. Then we use edge count to define which one is screw or which one is bow. Then return the level. If not, it will return the no object detected. This is the prepare image function. So we get the box of the image with height. Then we warp perspective of the image into vertical, and we separate it into crop image 1 and 2, which will be the head and the tip. Then we check if it's true. If not, we rotate. This one is for the transparent image or the transparent canvas to get rid of the error. So we're gonna make it bigger so the edge of the picture will not touch the edge of the object, avoiding errors in when finding edge or contour. And this one is the main process image function. So we check the part, get the image, check the image if we can load or not. Then convert to gray, convert to black white, use crossing, and this is the pixel to convert from pixels to centimeter, and then we find control. And this is the loop to find control for every object in the picture. And then we get the width and the height, convert to centimeters, check that. If screwable, get the dimension from the find dimension function, then classify which one is screw and bolt, then print detected and then resolve, then return the process image to the main program. And if it's not, we find dimension not, get the result, print, then return, same as screw and bolt. And this is just to check if we can successfully save the file or not. So this is the main program. So we define our webcam to cap, check if connect or not. Then we use the loop to start recording and show in the output window. And this is where we get the 3 seconds interval between image. And this is the timestamp which we will use to naming the file and then save the path. Then after saving the path, we will define the same path as the test image, which will be used to process in the process image function, and then save it as process path variable, and then save it into the directory over here. And this is where we can stop the program by pressing Q, and then it will stop. So this is the result of our program. So after we start the program, the webcam will start recording the video and then capture the image for every second. And this right here is the example of the both coordinate we'll be using. Then we get the process image function and we return like detected, type, width and height and the bounding box. And then this is where we save the capture image from the webcam. And this is where we save the process image after we use the process image function from the picture of the webcam.
So here's a C# window form application that reads data from a JSON file and display both text and image using OpenCV and mglue.cv. This program is designed to process and display information about bolts and screw, including their type, size, length, while also showing a corresponding image. So let's dive into how it works. So first, setting up the application. When the program starts, the window form initialize all necessary UI components, such as button, text box, and image box. This ensures that when the user interacts with the application, everything functions smoothly. So second, loading the JSON file. When the user clicks the Load Data button, the program attempts to read a JSON file from the predefined location. It first checks if the file exists to prevent errors. Once the file is found, its content is read and parsed as an array around, allowing the program to handle multiple objects. For this implementation, we extract only the first object from the JSON file. Third, extracting and display data. The extract data including the type, size, and length of the detect object. Each of these values is displayed in their respective text box. To ensure smooth operation, the program also verifies that the expect data field exists before attempting to use them. If any values are missing, it replaces them with a placeholder like n/a to prevent caches. So for loading and displaying the image, alongside the text data, the program also retrieves an image path from the JSON file. If the file is valid and the image exists, it is loaded and displayed using OpenCV functions. However, if the image is missing or the path is incorrect, an error message informs the user. So 5. Error handling and stabilities. To ensure a smooth user experience, The program includes error handling if an issue occurs while reading the JSON file, parsing data or loading the image. A friendly error message appears instead of causing the application to crash. So, in summary, this program first read a JSON file contain objects data, display the extract value in text box, load and show an image based on the JSON file path, handling errors gracefully to improve user experience. So the results show that when we run the Python code, it saves the result data as JSON file, and then we open the UI in the C# code and click the calculated button. The C# will appear the output data from JSON file, showing type, size, and length, and the image according to the output.
Then last but not least, proposed improvements. Our current project focuses on classifying both schools, nuts, and their size. However, real-world applications require handling a wider variety of components. For example, schools come in different head shapes, like star shape or past shape. Expanding our classification to include these variations will significantly improve the system's usefulness in industrial settings. Application to automation system. In a controlled environment, we can ensure consistent testing conditions. However, real-world automation presents new challenges. Changes in natural lighting, such as shifts from daylight to artificial lighting, can affect detection accuracy. To maintain reliable performance, our system must be robust against varying environmental conditions. Implementing adaptive lighting collections or real-time calibration could help address this issue. Enhancing system flexibility. For greater industrial adoption, the system should be easy to integrate and adapt. Optimizing the code to require minimal adjustments during setup will improve flexibility, making the system more practical for different industrials. Implementing a modular approach could allow businesses to customize the classifier based on their specific needs without extensive reconfiguration.